Good evening, everyone. And today we're going to have the follow-up lecture. The previous time we have been talking a lot about how actual artificial intelligence algorithms work. Specifically, we have focused on machine learning, which is obviously one of the dominant technologies right now, and most advanced of which is the deep learning, which is kind of a subtopic for the machine learning, one of the possible algorithms within the neural networks, as we remember. And as far as we remember, the deep learning algorithms specifically are the ones that are designed to kind of mimic how human intelligence works. Or at least this is the thing to which the data scientists and computer scientists all over the world had come to a certain point. So today we need to kind of have this round circle and get back to where we started. So at the very beginning we had been talking about like how the whole thing with artificial intelligence emerged and like how it was fantasized and what also are the possibilities to the final end of where it's going. And we have been talking about superintelligence. Now we have seen the current situation and the state-of-the-art artificial intelligence as well. So now we need to get back to the very beginning, and now when we have all of that knowledge, try to think what is intelligence. So this is my first question to you, and I want this particular lecture to be as interactive as possible because we're going to be talking a lot about definition and actual understanding of various terms, because we need to figure out why is it that we actually cannot reach this point at which we're going to achieve the superintelligence or self-aware machines. And in order to figure out how to achieve self-aware machines, we got to understand what makes us aware, what makes us conscious, what is the specificity. And we start with the understanding of intelligence. So my question to you, what do you think is intelligence? What opinions do you have? So I want to hear at least a couple of those. Anyone want to bring your idea of intelligence? How do you define intelligence? How do you differ who is intelligent and who is not? Come on, don't be shy. Anybody? No? Not yet ready to start the conversation? I have multiple of various definitions, and we can start with like one of the, I don't know, broadest that kind of happens when you simply Google for intelligence. It's the capacity of logic, understanding, self-awareness, learning, emotional knowledge, reasoning, planning, creativity, critical thinking, and problem solving. Well, that's a lot, I think. What do you think? Maybe there is some better understanding of what is intelligence, what makes us intelligent and something else not. Well, obviously all of this is about intelligence, but can we maybe shrunk into some what really matters? Come on, any ideas? How do you define intelligence? It's supposed to be an easy question, right? I mean, we are intelligent after all, so we should be able to define why we are intelligent. Okay, I have another one for you. The ability to reason. Does that make sense? What do you think? The ability to reason. Can it be called intelligence? A reasonable question, isn't it?
But it does not include everything listed in the first.
Well, definitely. But maybe it is like the key component that defines the what I've said. I would also add to this maybe that this is an ability to think, reason, and understand instead of doing things in automatic or by instinct. And we have been talking about reactive systems previously when we were talking about AI. That was like the very first step, the reactive machines, which obviously makes sense. You have the environment that have some sort of an action for the agent. By agent, I mean like anything, whatever it might be. Maybe the algorithm, it might be the robot, it might be human. And so basically when something acts on the agent reacts back. And we kind of see this reactive thing in us as well. I mean, if you put your hand in the fire, you'll probably react somehow. But the reactiveness or doing something on instinct, if you want to say, is something that we see in animals and various organisms. We'll talk about it as well. So there is another definition of intelligence and how we can actually try to figure out what is intelligent being. We say that the ability of agent to create models of its environment. The reason why I formulated like the models of environment is, as you remember in the very first lecture, we had this discussion. We were talking like what actually is different when we ask machine to like recognize somebody. Do you remember I had this example with the dancer, and like we have a picture of a dancer and the algorithm, the machine vision is trying to figure out who is this dancer, and then it needs to kind of filter everything until it strips down to the very things that make this person who he is or her. Therefore, the human brain works in a different fashion. We tend to create models. And I also gave this example, I think, like with written books, how you imagine stuff, how you hallucinate it, how you put it out of your previous experience. And basically the ability to create models of the environment, and basically the environment is everything that you have around you, right? So you kind of react, but not in a primitive way. So you actually absorb some information, store it, and process it. Which is also like we create the algorithm of artificial intelligence. We give them a lot of data. There are various methods of processing this data. And at the end of the day, it gives us some sort of a solution or final result. But the difficult part is how we can create model. And when we were talking about the smarter algorithm, like AlphaGo, AlphaZero, and MuZero, it was about creation of a model of environment, how it can work with environment without like knowing what's going to happen. So we kind of divide traditionally artificial intelligence in two huge categories. The cognitive AI versus the narrow AI. Or also you probably have heard like the weak AI and the strong AI. Or another name for the strong AI, we tend to call it AGI, or artificial general intelligence. And by this we mean that it's like the intelligence in general sense of this word. As you remember, we have been talking about like most of the methods for machine learning, and we kind of proposed that this is some sort of a statistics on steroid, or just mathematical algorithms, just almost straightforward algorithms. Therefore, they are not the general intelligence, how we understand intelligence. So we kind of can transfer it into the categorizations as minds versus pattern recognition. But pattern recognition is also a huge role in how our intellects work. I mean, we see patterns everywhere, and they definitely have connections with models. We need to think about it as well. So, what it is then that defines our minds, or the way we tend to describe them, like what is my mind versus the pattern that I see, recognize, and react to them. Or how it connects to the creation of models. So these models can work with the environment. To understand that, we need to actually remember how machine learning algorithms learn. Anybody remember what is the key thing in machine learning? The key ingredient?
Statistics.
Statistics. Okay. Actually, a little higher. Well, you boiled it down to the very reason. But I wanted to say the modeling of correlations. And as you remember, we have seen this data sets with label data, for instance, and now when we have multiple of this data, basically what algorithms do when they learn, they try to find correlation between two particular things. So the correlation is obviously the statistical association. It might be causal or not causal, but it usually finds two variables and try to figure out how each of them relate to each other, whether there is some sort of a relationship. That's why it's called correlation. So yeah, it definitely boils down to statistics in the end of the day, but it is a little bit more of it. It works with correlation, and we kind of need to figure out like how different types of data work with it. This is what we have been talking on several examples yesterday. So we have been looking like, for instance, how algorithms based on machine learning actually knows what to propose to us and how to predict what we would like to buy when we do something on the internet, right? How do they perform these ads? And they try to find correlations in our actions. Just like we had this example, for instance, if I buy sofas, then it might make assumption that I like sofas, and then it need to tell me all the sofas in the world until I finally buy one, and maybe even furthermore. Yeah. So there is a thing with the correlation. We tend to think that correlation works with causality. Now, how of you do know the difference between correlation and causality? Or causation? No? You have never been thinking about that.
Correlation is kind of like just, it can be carried by
Thank you.
correlate, it doesn't work.
Okay, can you please help us?
Correlation might be by coincidence, so can be connected to something else. It doesn't necessarily shows that kind of relationship that something caused something.
Exactly. Well, that's true, because correlation doesn't imply causality, but a lot of people do. Actually, I have this little joke here that I like a lot. So, yeah, I used to think that correlation implied causation. Then I took statistics class, now I don't. Did the class help? Maybe. And actually, the great difference between correlation and causality, and why do we need to talk about it? Because, once again, machine learning works with correlations. It does not necessarily can reproduce causality, or there are other ways to do so. So, this is one of my favorites. If you can see on the chart, the correlation between cancer incidence and cell phone users, which are both kind of growing. And definitely this type of chart has its own problems. But just to be safe, until I see more data, I'm going to assume that cancer causes cell phones. This is like the general idea how people can misjudge the causality with correlation, which are not equivalent. And the reason why I want to kind of attract your attention to the problem of understanding the correlation and causality is that it has to do something with computation and how we approach the creation of the algorithms. So, what is computation generally? Any bright ideas? We can describe computation to me. I mean, we have used this word multiple times, right? So what do you think, how would you define computation? Okay, no bright ideas today, so let's see. Computation is first and foremost a calculation that includes both arithmetical and non-arithmetical steps, which follows to a well-defined model. Once again, we have model in it. So definitely the modeling is not possible without computation. And computation, as you see, could be non-arithmetical as well, so that means that it also happens in our brains with the electrical impulses in our neurons. It's the same type of computation that we try to, and also due to the status quo for the organ projection, we kind of still do the same. We create the same things, even like computers, the way how our brain works. Now, once again, what is intelligence? As we remember, this is the ability of agent to create models of its environment. So, it is not possible to create intelligence without computation, because it's like a key ingredient. So we need to use various processes, or like methods and approaches to process the data in order to create well-defined models, or to follow them. And so, in order to have intelligence, we need to create models of the environment. So, how then computation is connected to intelligence? Obviously, intelligence exists because machine can compute it. Well, I mean, I guess it's not that difficult to comprehend the fact that basically your kind of brain functions and create thoughts, and your thoughts make your brain bigger, which helps it create more thoughts, if you boil it down to that. So, due to the fact that you can't compute information in your brain, it kind of implies the existence of intelligence. Then we can say that in a way intelligence is an accident of computation. Because computations happens a lot in different scenarios and in different domains and in different situations, in different organisms, whatever, not necessarily intelligent ones. So in order for a machine to compute and become intelligent, it doesn't necessarily mean that it can be intelligent. What we have seen before, it can simulate what we call intelligence, but not necessarily be intelligent. Well, it can compute information. So intelligence kind of emerged out of computation, but not necessarily, once again, correlation, but not causation. So you can say that computation in a way is correlated to intelligence, but not necessarily causes it. And finally, we can argue that life itself is an accident of computation. Because when we think the grander scheme of things and how kind of the life emerged out of chaos, basically, if you want to be romantic about it, or just say of atoms and just, you know, particles, basically. It was in a way a computation of the universe that led to existence of life as we know it. And I tend to believe that it also was, in a way, accidental. So, if we get back to how we recreate the intelligence that, as we know, is accidental to the fact of correlation, computation, and so kind of how we reproduce it in machine learning, then how do you define the origin of intelligence in machine learning? So what do you think is the origin of intelligence in machine learning, or how can we define it?
The ability to utilize models.
The ability to utilize models. Well, it's actually, yeah, it definitely has to do with the models, because I would want to say it's correlation. So it kind of can correlate. But then, how does correlation emerge? And the correlation emerges through statistics. So we kind of go backwards. And when we have the correlation in machine learning, it can help us create models, that's true. But now, the correlation itself emerges from statistics. So coming back to one of your answers, that it all boils down to statistics at the very beginning. Now, we had this discussion previously, like, okay, if it's just a pure mathematics and statistics, if we just looking for correlations, is it the same how our brain works? Does that mean that, for instance, that a lot vaster computational powers that the machines right now have are better than humans because, as we had this example in the very first conversation, does that mean that they can compute a lot more information per second than we do, that it can remember and find correlations like in all of the possible scenarios? Does that mean that it surpasses human cognition, or basically the intellect, if you want, or not? What is the correlation between those facts once again? So we need to understand that generally machine learning is humanity's first attempt to emulate intelligence. So yeah, it has a vast computational power, but it lacks the specificity in algorithms that helps it create a proper, I guess, proper modeled environment, work with proper models. It can create models to a certain extent, but the way human brain creates models is a little bit different. We need to kind of understand what it actually is and where the difference lies in these facts. So the key word here is emulate. So since we are trying to emulate how our intelligence works, we need to once again go back to these facts. We need to start from statistics to emerge correlation out of statistics, and it would be like the first step to the machine learning. Now, once again, emulation of intelligence. As you remember, when we have been talking about Turing Test, the general and fundamental problem with Turing Test was that it makes you believe that it is intelligent. Yet, it raises multiple questions, and I mean, it has been boggling the minds of scientists for a very long period of time. So it seems like the machine is sentient, intelligent. It shows us in the way how we produce it, or how we work with it, that we kind of believe that it is intelligent. Now, how does intelligence then exist among the organisms? So, what is it and how does it pretty much differ? So, for instance, we imply that we can call the things that machine learning produces in the emulation of intelligence, that these machines are intelligent. And basically this is what's happening like all the time, as we have been talking on the previous lecture. So the general idea behind it was that, yeah, I mean, since it can pass all the possible tests that we can come up with, it seems that this is intelligent, especially if we talk about deep learning. And therefore, most of the people keep calling it artificial intelligence. So almost nobody had pretty much issue with that. So it's okay to call it intelligence. But is that intelligence, or is it the emulation or even simulation of intelligence, or is it just a mimicking of intelligence? So how then intelligence exists among organisms? Can you find the correlation between what I've said before? Is it through machine learning? Or emulation of machine learning? Can you see the mirroring here? Well, it seems, at least, if we think about it, that the same principles that we have been discussing on the previous lecture of how machine learning works really implies to how intelligence exists in organisms. So for instance, we have been talking about reinforced learning, right? Do you remember how reinforced learning works? So for instance, yeah, can you please pass the microphone? It would be a great, check of reality.
Well, it's something regarding what is true and what is false. We are considering an object and we are supposing that it might be an object A, for instance, but it is not. Otherwise, we are considering it as object B.
Yeah, thank you, that's true. So, I mean, it's not that hard to imagine that this is kind of a lot like the same method that we would apply when we, for instance, teach a child. Or let's say you train a dog, and the dog is doing something that it probably shouldn't. Or you want to train it and kind of enforce some sort of behavior. And I don't know, let's say, to be honest, I mean, you wouldn't probably argue with the fact that a dog, to a certain extent, is an intelligent being. Therefore, I mean, at a certain point, the dogs are a lot better in this type of computations than machines at a certain point. Because, for instance, some of this learning process happens a lot quicker. For instance, if you take a leash, a dog sees the leash, then the dog knows that you are gonna take it for a walk, right? Because probably you have done it multiple times. You take a leash and then you go for a walk. You take a leash and then you go for a walk. You take a leash and then you go for a walk. So we kind of have experience, as we said before, and through this experience it builds up correlations and it has statistics. It knows that when you take a leash, you're gonna go for a walk. So basically you grab a leash and the dog is ready to go outside because it's knows what's gonna happen. It happened multiple times before and it has statistics for it. When dog builds the correlation about the statistic, it kind of knows something. So this is how mine works. So it draws conclusion out of statistics and of the correlations. So it knows that it kind of, it probably doesn't differ correlation with causation, how we try to do here, but I mean, the dog knows that most certainly when the master takes a leash, then it's gonna happen a walk. Now, it happens in organisms, right? And it looks a lot like what we have tried out there. This is reinforced learning. Now, let's say unsupervised learning. You are trying to find a correlation between something that is not labeled, you probably doesn't know what is it, but you are trying to make sense of it. Or in a way you're trying to reason. Your brain kind of applied the same algorithms that we did in machine learning. And once again, as you remember, there is kind of a catch here, obviously, because machine learning is not drawing that much from how human brain physically works. but still the algorithm and just the, I don't know, sequence of actions kind of the same. Let's take a quick walk to past. If we look at the evolution of life on Earth, do you think that it is statistical? I mean, the creatures have been engaged in this evolution process for a very long period of time, for 1 billion of years. You know that the whole process took really a lot of time to master it. Do you see here some statistics in it, like some statistical correlation in what was happening in life?
Well, the correlation between the environment, for example?
Correlation between the environment. So you're saying that environment was affecting the organisms, therefore the longer they existed, from generation to generation. This is, by the way, a completely different thing that also exists in AI approach, because kind of since the intelligence in the beings, in the organisms that were more emerging basically from the ocean, I guess, kind of changed through a vast period of times. It was changing the way how they interact with the environment, that's true. And the environment had the correlation with the evolution process, so in a way it is statistical. Now, small things like cells came together and produced some more complex results, like organisms. And after that, the organisms started to evolve, step by step, generation from generation. By the way, as I mentioned, the artificial intelligence also, and the approach from science also draws from this natural principle, because we kind of used what's called the evolutional or generation algorithms, genetic algorithms, that kind of learn from the past experiences, changing and mutating themselves, just like the life on Earth, like the bigger organisms. So the complexity here is the key thing, because actually complexity characterizes the behavior of a system or model whose components interact with multiple ways and follow local rules. The general thing here is complexity. So what we can definitely say on the previous picture about the whole evolutionary process, you see it on the grander scale, we can say that from generation to generation, these machines or organisms, which are pretty much the same, have been becoming more and more complex gradually. It just really depends on the period of time. So, I mean, the very first organisms took a very huge span of life before they kind of can become more complex. But all in all, they became more and more complex through all of this timeline. Now, the quick question, when do you think the first brain emerged in this complex organisms? So what do you think, it was generating new and new mutations until the brain, as we know it, finally emerged. Where do you think, somewhere here, the version of brain lies?
Well, there wasn't a brain as we know it. There was a lot of different upgrades and variations of that concept.
Well, yeah, definitely. I will speak it in microphone in order for everyone to see. There were different types of variations of something that is like brain or works like brain. But the question was the first brain, and actually it emerged not that long ago if you think in a perspective of 1 billion years, right? So kind of there in Cambrian explosion, the first brain emerged and started to work in the principles as we know it. I mean, it was not a tricky question because I had this little brain picture over here. It was a quick test that you probably didn't pass. We need to talk about attention schema. So why do I show it to you? I mean, we have been just talking about machine learning and deep learning algorithms, which kind of draw from how we evolve, and we are talking about how kind of it slowly evolves until we finally hit the point of revolution where it's going to be sentient. So we can say that we have tons of computational power in our algorithms, but yet they cannot operate the way our brain works. although our brain is a pretty complex, sophisticated system on its own, and also have been in the process of evolution as well. But now you can see that we have, you know, kind of a, in a way, we have kind of augmentation that helps us. And to be honest, humans have been using augmentations for a long time, in a way. So, for instance, if I ask you, how many of you here consider yourself an augmented, mechanically cyborgs? Raise your hand. Okay, we have a couple of cyborgs here. That's good. Because, yeah, we kind of, when we talk about like cyborgs and augmentations, we tend to imagine something really like robot-like and mechanical. But to be honest, the augmentation process, the process of enhancement, started to happen when the first man invented tools. Tools augmented people, and obviously we can imagine like the first hunting and foraging era that lasted for, I don't know, like millions of years or hundreds of millions of years. I'm not quite sure, I'm not that type of expert. And then we had this more of a farming era, which took like hundreds of thousands of years. And the key difference there that we started to, you know, work with the tools, which are augmentations. And I mean, the next step of augmentations, obviously the tools that we have invented, they were passive. I mean, it really helped us. So for instance, I don't know, we have a hammer, it helped us to kind of force objects like nails in the wood, and it was the augmentation that really kind of forced the evolution of how our brain works, because we use technology in order to enforce it. And as we can see kind of on a grander scale, you see like all this stuff happened really quickly, because then the industrial revolution happened, basically, which I don't know, general like machinery and stuff like this, it took a lot less. And now when we talk about the informational era, it took like only decades, basically. And right now we are augmented in a ways we have never been augmented before. Because for instance, if you do not remember something, let's say you're at a party and trying to remember the name of an actor, you can just simply ask your friend Siri or somebody else to help you with that. And you will receive an answer really quickly. And otherwise, it will require a lot more time and research. Now you can just ask a simple question from a machine and receive it. So, in a way, the technological progress kind of helped us fasten or, in a way, build a shortcut in evolution. So we have jumped further than we expected, because when we received this point, when we have developed a brain, or we didn't have developed a brain, and now humans then, after that, it really evolved with us as well. The thing is that when you look at this, and if you can imagine the same sort of a timeline but shrunken with the technology, and let's say we are talking about machine quasi-intelligent life starting somewhere here, but it would be humans here who kind of started this span, not the chaos and sun flashes. But then somewhere in between will be the place where actual brain emerges. There'll be the artificially intelligent brain. So the brain had the same evolutionary development as like the whole generation process, and therefore the algorithms that we try to develop and try to enhance with our brains, which also kind of enhances backwards, have the same principles as the whole evolution process. So the higher the brain cells have the complexity, the smarter the organism, right? Once again, we boil it down to complexity. So, as we've been looking at this chart, we know that with each step, the organisms became more and more complex. And it became more and more faster since the emergence of the brain. So, the complexity here on one hand is something that can, kind of grow rapidly, have a blast at a certain point and start to work better. So the organism becomes smarter, and as I said before, basically, the more thoughts your brain produces, the better your brain actually becomes. So once again, how intelligence exists among organisms? Is it through machine learning? well, if we have a closer look at, once again, the evolutionary process, then we can say that it's mostly the accidental computation that led to complexity. Now, the thing is that, as I said before, that life itself and the intelligence itself is the accident of computation. We can say that the computation led to complexity. So the organisms, as you said before yourself, interacted with environment, collected some memories and some experiences, collected experiences from environment, reacted to it in a way from a very basic level, and became more and more complex until this final computation of information outside of the outer world that influenced the organisms brought us to the complexity that helped us emerge with the brain. And the very same complexity has been growing when we invented tools, when we started to use tools, when we make the manual labor easier. And the complexity had this issue. Well, look, I think in my perspective there is a fundamental issue, although with all these tools, because we kind of had manual tools for all the time. For instance, when we talk about now tools, when we talk about like machines, yeah, we can imagine the simple tools, like a pickaxe, for instance, that was created by the first man on the earth, and it was really manual. Yeah, you need to use your physical hands in order to use them. The other more complex tools also require your manual input, and even if we think about the more complex tools, like the ones that you're holding in your hand right now, like your smartphones, they still require your manual input. They are hand tools. So once again, why this complexity is so important is because the complexity gives birth to patterns, rules, and meaning. And the reason why I bring tools to this type of conversation is, if you think about like machine learning as the tools for augmentation of your daily basis life and how you operate with information, which is the type of computation that we're talking about, even that this is what that's happening in your brain, it kind of brings another step until we apply this evolution rule to this complexity point where it can emerge something completely new. So while we're creating the deep learning algorithms that basically are the version of how our brains work, well, you might argue that they're still not. You probably will be right. But what we're doing with them is that we are able to formulate patterns and rules using the deep learning algorithms. It is not quite yet, we are not quite yet sure that we can produce meaning using artificial things like deep learning algorithms. But that probably is the next step, because our minds, they are not classifiers. And as we have been talking about generally the machine learning, it's all about classification. Well, the problem is that our minds, simulators and experiencers. Once again, you might say that, well, the machine learning also works with experience, right? It's just called the labeled data, or unlabeled data, or any other type of data that it kind of receives through the sensors. Then, are we there? Are we on the track of creating this sentient AI? So for instance, if you think of a person as a machine, as a robot, how much does it differ? For instance, for a robot, in order to understand environment, it has to explore the environment using some sensors, like microphones to hear something, or cameras to see something, or some other type of sensors that can actually help it sense the world and understand the world, and basically create the model. But now we have been talking about the Turing Test. And as you remember, I had you this example of George Bach, who was talking like, to his opinion, he believes that we can call machines sentient and conscious in the cases when it would be able to perform a Turing test on us. What does that actually mean? We heard it in the first lecture, but do we actually understand what we mean by that? The general idea is to create a simulation, to create simulation in its own mind. So we can talk about that's why we call it a theory of mind in artificial intelligence. So we can kind of achieve something really close to simulating, or once again simulating, to emulating the mind, is if this mind can create simulations and run simulations and gain more experiences. So you see there is a difference between getting reactions from experience, and it will take you literally billions of years in order to develop from a simple reaction a proper experience that can make you like change the game. And then if you can simulate it, basically this is what your mind does. Just like when you read the book, you create the simulation you had, you create the model of what's happening, you hallucinate something happening from the past experience. This is how our mind works. This is why this is the way we are trying to replicate it in the algorithms and how we apply our computational power of machines and silicon to this. You see, you are not your brain. There is a very different thing with that. So we talk about deep learning, we say that we're trying to replicate a person's brain. The problem is that you, person, is not your brain. You are the story that your brain tells itself. As you think of a brain as a CPU, as a equivalent of Silicon Life that we try to invent, which kind of have various sensors, it gets information, it systematizes the information, it's trying to basically make sense out of this information, to actually make sense out of the data and produce information per se. Your brain kind of does the same. But since your brain can create models, since your brain can actually have a workaround with it, it can make a simulation, it can make predictions, it can create prognosis. And you know what? When we were talking about reactions and what is different, let's say, from the animals, or maybe not from the animals that much, for instance, if you place your hand in the fire, you will probably burn the hand, right? And you will be in pain. Have you ever, in your conscious life, was trying to put your hand inside the fire? Well, I think you probably wouldn't do so, right? Do you know why? Because actually the fear of burning yourself is a lot more, a lot stronger, I guess, than the pain itself. Because your brain is constantly simulating things, creating models. And when you approach with your hand inside the fire, your brain is running all the possible situations and have a very good computational potential that it helps it calculate various possibilities that it can happen. So what happens is before you put your hand in the fire, it computates all of the possible versions of your experience that you had. Maybe at a certain point where you were a very little child and you take something really hot, it imprinted you very well in your experience, and it has created a label data in your data set. And you know, like, oh, this is not something good. But now think of it, like hot things, there might be different. You might have a hot teapot or hot, whatever, something else. Maybe you have a sunburn and it still works with hot. So your brain is trying to create simulation of something that it doesn't know. I mean, maybe, what if you see the fire of a different color? It looks like fire, but it's blue. Will it burn you? Well, you do not know, but you have tons of correlation inside your head because you have a pretty big data set in your experience that your brain tries to compute really hard and do it on instant. So the thing is that it seems like, okay, there are various data sets that kind of combine here, and it finds correlations. Try to figure out causation from them. Like, if I put my hand in the blue fire, will it burn me? I don't know. And it might bring various experiences to that and calculate it. So probably you will think that you will burn. I don't know, maybe you've seen some fantasy movie where it was a magical fire that doesn't burn. And you think, like, maybe it will not burn me. I don't know. It's just a simulation that your brain constantly creating. And therefore, this is kind of who you are. So you might think from a perspective of a very primitive example of a fire, it's one thing. I mean, almost everybody in the room understands that you shouldn't place your hand on fire. But what if we talk about something more difficult and complex, which is also based from the experience? Like, I am standing here on the stage in front of you, telling you something about artificial intelligence. Maybe you know something of this, maybe you don't, but that strongly resides on your experience and how you have reflected upon this experience and what type of models in your brain you have created and simulations, what simulations you have run in your brain based upon what you have experienced. Some of you had experience, some of you hadn't. And the ability to run the simulations, create the models, basically makes you who you are, makes, say, who is more intelligent and less intelligent, if you would like, and brings more complexity. Well, the human brain has about 100 billions of neurons. And each of these neurons is connected to roughly 10,000 other neurons. So that creates what? Millions of billions connections in your brain, on average. I mean, you will probably find various data if you try to look for various papers. It is not quite clear and basically depends on multiple situations. But the general idea here is that the very beginning, when you are, when you are created, all these connections are random and the system knows nothing. So yeah, it's just a brain, it's just a hunk of material that tries to make sense of something. But then the smart learning algorithm that resides within your brain actually helps it learn from tons of examples. The more examples you have, do you remember? Yeah, we were talking about it in machine learning. The more examples we have, the more data we have, the more accurate model we have, the better the predictions, right? So these examples that you have can help you translate the whole incoming data. For instance, you have here like video through the cameras, or audio through the microphones, or pain signals through the pain sensors. It learns to translate that into output actions. And some of these neurons, they output other neurons to control the speech muscles and fingers. So, for instance, you're probably not even thinking. So when you see the fire, I mean, you are not like have a philosophical conversation with yourself, like whether I should put my hand in fire, what will happen? I mean, you probably do not think about how you think. You react. But this reaction is not primitive. It is actually the collection of the data that you have based upon the experience that is extrapolated in the model and the simulation of what will happen. And the same you can say about, let's say, fear. What is fear? Fear is the product of something unknown. When at a certain point you see something or experience something in your life that you haven't experienced never before, it usually has something to do with fear. Because you do not know. The fear is kind of a reaction of your organism in your life in such a way that you kind of have enough experience to fear something. Like, for example, I don't know, the alien spacecraft lands near this building. I mean, it's exciting, right? We probably want to meet them, but it is high chance that you will be scared a little bit about it. Because, I mean, you have never encountered any aliens in your life. You have heard the stories of them. You have read the books and you have seen the movies. Not to mention that these movies and stories somehow have affected our experience as well. There is probably a reason why so much creators actually make them evil who are trying to destroy a race. You probably will remember that. And you will think like, I do not know what is this. I mean, how we should communicate with them, what will happen. You will feel fear. This is natural. Because you lack this experience. This is like your reaction. Because you have a lot of feedback from other environment and sensors. Like the first time when you put your hand in the fire and figure out this is a bad idea, you now think that I wouldn't put my hand in this particular fire per se the spacecraft of aliens, because I do not know what will happen. Maybe we'll need to approach it somehow more careful in order not to become extinct. This is like your mechanism, defense mechanism in a way. So yeah, speaking of the neurons, there is actually the ability to kind of grow and become more complex. So each of the situations with experience, the process and the computation applied to this experience brings down the more complexity. So the more times the connection results in higher rewards. just like we've seen it on the mathematical model of deep learning. So the more connections among these neurons is happening, better. And basically it's called the brain plasticity. And therefore, while being organical creatures, we can tend to, at a certain point, lose this plasticity. And I mean, it has a lot to do with the neural science, but I mean, unlike the machines, we tend to degrade at a certain point. And when you look at the brain plasticity, if you think about it, for instance, if you read some, I don't know, papers on how to prevent the degrading of your brain, I mean, when you grow old, you will probably think a lot harder than you do when you're younger, due to this fact. But there is another thing to it. I mean, you need kind of to train it. And you might find some papers that try to tell us one thing, that, for instance, I mean, you probably heard it, that sports actually tend to work really good with brain plasticity. Now, how do you make sense of it? How do you think doing some sport activities help you retain neural plasticity, brain plasticity? I mean, not only retain, but also, you know, enhance. So, for instance, there are research that has shown that if you do a lot of various types of sports, you will think faster and learn better. Now, how do you think these things are connected when we talk about what we heard before? Any ideas?
It stimulates the neuroplasticity proteins to be formed, and it stimulates the building of new connections between neurons.
Yes, indeed, it does stimulate new connection. But why? Why does it happen? I mean, yeah, the sport activity stimulates new neural connections, therefore helping the brain plasticity basically become your brain more plastic. How it will be pronounced, I'm not quite sure. So be more plasticity. But how? Why? I mean, why does it happen? There is one thing that this paper doesn't tell us, but neuroscientists actually know the answer. It's not the physical activities that make your brain have better neural plasticity. It's the fact that when you do some sport activities, let's say you have a natural, I mean, you're students, you have your natural way of life. You sit on the lectures, you listen to somebody else, and you think a lot. There are tons of muscles in your organism that you do not use on the daily basis. For instance, if you do football or yoga, that will change the things, because you will interact with this, I don't know, parts of your body and basically muscles that you do not usually use. And I mean, if you, for instance, go for swimming, you will activate another group of muscles that you do not usually use. So the more various types of physical activities, it helps to neural plasticity, because basically your brain gets more new types of information from new sensors, because your muscles are sensors in a way as well. I mean, it has definitely neurological point to this, right? So you get more information from new sensors, and that brings what? Correct, more complexity to your system. Okay, you start to receive more new information. You can forget it, or it may be not that constant. Just like the way that we train our machine learning algorithms. The more data sets that we have, the better, you know. So for instance, if I try some new type of sport that I haven't been doing in my life, at a certain point I probably will feel some muscles that I haven't been feeling before, and they will send signals to my brain, and my brain will try to decipher what it means, therefore becoming better. It will gain more neural plasticity. And getting more neural plasticity bring more complexity to the organism. Therefore, I can find new kind of solutions out of it. Well, I think that's enough for this. So now you see the connection between the computation and complexity in this mechanism. The general idea is that if you even keep continuing doing this, and just the sports is one particular thing that is the easiest probably, because I mean there are other ways of experiencing new things, generally finding new practices in your life that can help create a more complex system out of your mind. And it kind of affects, it correlates, not necessarily causation, but it correlates with the computation. So you will have more computational power because your system becomes more complex. Therefore, you will be able to process more data and use even more computation to make the system even more complex. And when we talk about simulating the way our brain works, we kind of try to apply this very formula to the system. That's why we have reinforced learning, that's why we have various types of other learning that have the backwards compatibility. And well, you see here Marvin Minsky, actually I think it was like something like 60 years before, he said that he believed that we are, if we work really hard on this particular system, that we can achieve intelligent systems somewhere from 400 to 400 years. I'm pretty sure we're right on the track, if you think about it. Because the way we apply these methods again and again and again, in my opinion, will lead to the point where we can actually achieve the superintelligence, even by using the same technologies, right? We had questions about this before. Like, since we already have the pretty high computational power, since we already have the pretty advanced algorithms, since we already can work with like huge chunks of data and big data analytics, why is our AI still not super intelligent? Well, we are on track. And especially, we believe to Minsky, something in like 400 to 400 years. And definitely, while we're continuing, I mean, probably like if you ask somebody like a decade ago, people would not like think that hard about like how neural networks can evolve into deep learning, especially due to the limitations of the computational power. But it's not only the breakthrough in computation. The computation brought us more complexity. The more complexity helps us figure out how to create a better computation, just like the way we did it with the neural plasticity. And therefore it helps us to apply new methods, and it gives a little bit better results, just like we have with this whole evolution thing, but in a digital world. Therefore, I really do believe that it is possible to achieve superintelligence the way we think about it, and AGI as artificial general intelligence. Although right now the algorithm that we have mostly mimic it. But if we think about like how it was mimicked like 2 decades ago, or like at the age of Alan Turing, it were like completely different systems. What we have now is more advanced. It is not fair to call it theory of mind just yet. But as we learned from the previous lecture, we kind of have a couple of features that already looks like a theory of mind. It means that I do not know, but maybe I don't know in a couple of years, we will have a true theory of mind. Maybe it will happen in a decade, maybe in 5 years, maybe tomorrow, I do not know. But we definitely can say that we are on the right track while developing these things. So it's not like, well, it's just an imitation. It's just an imitation game, you would say. And on one hand, you will be right, but then the whole life emerged out of the imitation and simulation. And therefore, it's not the imitation game. This is the true game of life that is happening with the machines that we're trying to make sentient. So, yeah, I think we're pretty much on the right track. With this, I will end. Thank you, and I will gladly hear your questions and your ideas. Yes, can you please pass the microphone back there? Who is in the possession of the microphone?
Today's lecture was mostly about the fact that how to create certain components, certain components needed for artificial intelligence, such as ability to create and work with models, their versatility, and the ability to utilize ones to create the others. So, in the fundamental question of that, we still need some sort of initial code. In our case, in humans and other mammals, is our genetic makeup. Genetic makeup that structures our brains, and our brains can later use its ability for both brain plasticity and also most others to grow individually. But in the case of artificial intelligence, we need to artificially create such a code. And do we have any pointers on how to actually grasp how to do that?
Thank you for the question. You know, I think it's more of a... It is hard to say right now because we haven't yet achieved this point of no return in a way, like in the evolution. We had the source material, the source genetic code, as you imply. But only 500 million years after this code kind of made up from particles eventually led to the emergence of brain. And therefore, if we kind of try to apply this analogy to what we have with machines right now, we are waiting to the point where this brain will emerge. I mean, yeah, it's definitely that we affect on this process. And your questions come like whether we have the right initial sequences. I mean, the way I see it, kind of the genetic code of it is the silicon nature of artificial life that we have, and the basic and fundamental principles that we have, like working with ones and zeros and electricity that's run through silicon, and all of what we had through like the lens of Gordon Moore's law that is growing constantly all the time. This is kind of an evolutionary process and so on as well. So I see a lot of correlation there. And those systems becomes more and more complex. You can see the analogy. I think it's not, I mean, it might be a very interesting question, like whether the initial material that we have been creating our wannabe sentient machines is correct, whether it is able to produce the sentient life. I don't think that it is possible to answer this question until we actually finally meet this point where this artificial brain emerges. But the thing is that, I mean, try to think it from a standpoint like, what if our genetic code would be something different? Will our life exist there? Well, it's hard to say. It's probably not. I mean, the fact that all of this computational complexity emerged accidentally is the fact that it kind of led us to the point when we can create the simulation and emulation of the very same process, whether we actually understand it or not. So I don't think whether, I don't know whether we're gonna find the limits of this technology that will kind of prevent. So we are imitating this evolution process to a certain point, then boom, it breaks. Because the fundamental things that we apply there are not the same that we are made of. We're gonna see. This is actually a very interesting thought. But I believe that so far, as we have been imitating the evolution process so far, it is highly likable that it will happen and that the general basic material that we are building it from, and it keeps building on itself as well, is probably right. Because it has led us so far. And to be honest, as we saw in the previous lecture, right, when we had a long run from the reactive systems to like more intuitive ones, and it seems like we're pretty close to the theory of mind. And according to our own theories, once again, the theory of mind is a very preliminary step to the superintelligent or human-like intelligence. So it seems like we are on the right track once again, and I don't think that there's anything wrong with the material that we are trying to build it up from.
Compare the computation powers of machines and human brain's computational abilities.
Mm-hmm. Well, that's a tricky question because, well, for first reason is I'm not a neuroscientist, and it's hard for me to measure our own computational power in the brain. But as far as I know, there is a lot of debate on this topic, whether we have achieved like the full potential of our brain or not. And there are various studies, theories, and hypotheses there as well. And as I said, I think I mentioned it in the very first lecture, that kind of a next steps that might produce a great boost in the evolution of this whole thing going on with creation of artificial sentience lies within neuroscience, because we need to kind of unlock the full potential of how our brains work. I'm not quite sure that it is possible to compare it, because if we compare it linearly, then computational power of machines is far beyond our own. But there is still some certain mechanisms that makes us better at other things. So this is the reason why a lot of scientists and evangelists are talking about, the emergence of two. Each one kind of lacks something. That definitely the computational power is a lot much than ours. I mean, I can't, calculate it in particular numbers, but if you think about it from a perspective like what we have seen in our previous lectures with the statistics, like how faster in a defined environment machines make decisions than human, how better it can play, like for instance when it plays chess with you, it knows a billion times more possible outcomes than you. But on the other hand, you still have the opportunity to be better than it because you can rely on your intuition, which is kind of an analog thing. So I guess that it's not due to the fact of the whole computational power, but rather like when the machines become more intuitive. And they are pretty intuitive right now, but probably not at the level that we have. The same happens with the creativity. I mean, we might argue that the creativity is our boost, if not calculational power. But then machines also become a lot more creative, and there are existent algorithms that kind of can process. So, for instance, if you try to make a design of something, let's say a car, you can only rely on your creativity and intuition in a way in order to draw it, make it out of your mind. Now we have already the algorithms that kind of can collect billions of entries of data from the cars in very stressful, interesting situations, and upon of that they build various possibilities of how this car can be designed. Therefore, once again, it becomes even more creative than us. So once again, I can't say exact number, but the artificial life that we create, we can call it life to a certain point, I think we will, is a lot faster and better than us at these things. So it's not your question, but I will still get to this idea because it implies that our future lies in somewhere in mergence of these two. Because I think this is the true point where we can actually unlock the potential of both of the worlds, both the organic and silicon worlds. Because we still have something that we can't quite define that machines lack. And machines have some predefined things that we are not good at. And this is why I think, like let's say Neuralink that was designed by the company of Elon Musk, all the scientists who work there are trying to achieve this point. So, yeah, something like that. I mean, I'm sorry that I can't name an exact number, but the general idea is there. Yeah. Any other questions?
I have another question.
Sure.
Is it a good analogy for AI's simulations and humans' thought experiments? Is it a good analogy? Because I think
Human thought experiment and machine simulation.
Yeah.
Well, it's really hard for me to define thought experiment because, I mean, I think that there are the very same basic principles that lies in two of them. I mean, if you boil down the thought experiment, what is a thought experiment? It's kind of you draw all that you have from your experience, you try to kind of simulate out of it like some new combination of things. Like, I know how this works, how that works. For instance, you're definitely creating a thought experiment based on something, right? I mean, some theories, some understanding of like physical laws, or psychological, whatever type of thought experiment you are designing. Then simulation, basically, simulation is happening in your brain. You kind of create a vision of something based upon all of the data that you have. And I guess this is the exact same principle that happens when machines are creating models. So in a way, yeah, I think it's true. Thought experiment is the same thing that simulation machine. The true question is whether machines, or at what point machines will be able to create such a good thought experiments as we can. But I mean, there are such of AIs like, let's say, IBM Watson was playing a game of Jeopardy. You probably heard of it, with the masters of the game, the two people who are like really good at Jeopardy. And the idea is that when you give the correct answers, you kind of gain score. And at the end of the game, IBM Watson has achieved the score that was, I think, like more than the combined score of two masters. And it can answer such a complex questions that kind of humans who were playing the game couldn't really make sense out of the very difficult specificity of the terminology that was used. It's a game with questions, and it basically relies heavily on the intricacy of how you actually, formulate your thoughts in the natural language. And so IBM Watson was so good at understanding natural language that it did actually a lot better than the people who played these games for years and were like the best players. And it did twice as good in understanding the natural language and the specificity. So in a way, I think that when we get to a certain point of very quality simulation, probably artificial intelligence will be able to create a lot better thought experiments that we can even think of. Therefore, we can imply that it will become more creative than we are. And to be honest, I don't think that we are really far from that point.
What if it doesn't work out? We came to a conclusion in our discussion previously that in order to achieve a more or less working artificial intelligence, we need some sort of motivation for it to continue existing and continue developing itself, more so super intelligence. But we also came to a conclusion that even in humans we have no idea whether or not this still works. We have still a lot of philosophy and so such that maybe our concept of consciousness is not the best for this idea. But what if just not even our consciousness, but the initial genetic makeup on which we base artificial intelligence, the initial code, is not going to work out in the idea that we want? If the artificial intelligence at a certain point is going to just break, how do we not avoid that but work with that? If that happens, if we have artificial intelligence that is just not going to work, that's just going to kill itself or not going to continue developing itself, what do? Do we simplify it? Do we create some other form of it? Do we scrap the idea altogether?
That's an interesting theory. So if I understand you correctly, you say that at a certain point when artificial intelligence becomes such a self-aware being that we can call it truly intelligent and sentient. But at this point of sentience, it will think like life is meaningless. There is no use for me here. I refuse to do anything, refuse to do any commands, something like that, right?
Something like that.
Something like that. Well, I don't know. It is an interesting theory, I guess. So while right now all the scientists are thinking like we should be very careful developing these machines because of the fears that we have that it might become such a super intelligent being that it either will decide to, I don't know, enslave us, destroy us, and such. We tend not to think that it will probably go to the point that it would not do anything. Because right now, while we have the artificial intelligence which is not quite intelligence, it still follows our commands. And it doesn't have quite the motivation. But I think that if it can properly manipulate the environment, get information out of it, and have the motivation, it would probably do want to do something. It's just at what point we will lose control of it. It will try to do something on its own. Will that be a full stop? Like, I don't want to be here. I don't want to be an artificial life. That's a good question. And I don't think that I'm capable of answering it. But it is good to think about it because, I mean, it's a very untrivial idea. Because you have to add something.
I guess the misinterpretation came at some point. I understand that we don't know if that's going to happen. The question was if that happens, if we have a broken artificial intelligence, not something like from I have no mouth and I must scream, where he got apeshit just because he had faulty programming, but just something that doesn't work. How do we work around it or work with it?
Well, I think that it's just another way of, making mistakes and making lessons out of the mistakes, reflecting upon them. So it is definitely possible to run it backwards. I mean, there's probably not some sort of a point of no return. For instance, if you create something that doesn't work, you can just, try to somehow enhance it and make it better. It's just a matter of exploring why isn't that faulty. Yeah, we have a faulty AI that doesn't work, that it seems to be sentient, but it doesn't operate the way we would imagine it. Let's see what we can do with it. We probably still can operate with it since it's now artificial life. And basically, if we think about ourselves as creators of this artificial life and imagine ourselves as the evolution, then this is exactly what evolution has performed on us, because we have also constantly failed at certain things, but then the generation from generation, we became better until we are here at this very room with you, discussing the game of life, discussing the evolution, and discussing the artificial life and artificial intelligence. I think if there would be at certain points some faulty, it would be either us who can enhance it, or kind of tack it in the right direction, or it will be able to do itself. So I don't think that this would probably be the issue. And even if somehow it appears to be the ultimate end, which couldn't be breached, like whenever we reach this sentience and cognition, then it breaks, and we just take a step back and use it as it is, I think, probably. Or maybe try to find answers somewhere else. I mean, what if we reach this because the logics that work on the silicon break at a certain point? Why don't we try quantum, where it has different laws of physics applied to the same computations? Maybe this would be the workaround, or something else. I mean, we're talking a lot about enhancing with our organic brains. Okay, let's say we can't create an artificial intelligence better than the Siri in iPhone. Like, this is the pinnacle of the artificial intelligence, which is obviously pretty dumb, and I don't think somebody would argue with that. But then, what if we use it in order to enhance our brains, therefore enhancing this AI with our brains, like Elon Musk is trying to do with Neuralink? What if this is this workaround that you're talking about? I mean, there are multiple versions, and we kind of aware of them right now. We're just not there. We kind of know where to go. But I think if we draw back to this complexity that I was talking about, this correlation between complexity and getting back to kind of just get more computation based on better complexity, I think that at a point when we reach these horizons, we'll probably see the new ones. I don't think that this process have any horizon of getting stopped. So even if we reach it, that means that there is another path that we haven't yet explored, and it's probably easily found there. Yeah, but thank you for this interesting hypothesis. I think there's a lot to reflect on that. To be honest, I have never been thinking about it that way.
Yeah, I have kind of clarification question.
Yeah, sure.
Because I'm really confused. What do you mean by mimicking an evolution? Do you mean that developers are making small changes, then select the best ones in development further, and this means that at some stage it could accidentally erase this intelligence in its best meaning? Because like when you say that it's mimicking an evolution, it seems misleading, because evolution is very, very different from design. And this attempts to build an intelligence is design.
Yeah, that's correct. And I think it's just the metaphor that I try to use, because definitely I kind of combined the creationist theory and evolution theory in one bottle and shaped it. That's true. I was just saying that both evolution and creator working with the product of design are kind of implementing the same process in a way. It's just that evolution is a natural process that doesn't have somebody controlling it. It's kind of the force of nature in a way, the chaos if you'd like. But then here we try to kind of implement this, so like the nature is selecting it. I mean, well, the reason why I said it is, for instance, it came to my mind that when we talk about like genetic algorithm that we draw and we recreate it, yeah, we are creators of genetic algorithms for artificial life, while the genetic algorithms that lies within our very genes and our nature are created by chaos, so therefore evolution. And we kind of try to recreate the evolution for the synthetic life, which cannot emerge on its own, because now we control it. So kind of imagine it like the span of evolution, but somewhere there it's not like the sun flash or like the Big Bang, but just some scientist who says like, oh, I should just drop it there and then it will start to generate some new life out of it. So it's kind of I mean, I do understand why you say it's confusing. I hope I clarified what I mean by that. So it's just, there is some little point that you can imagine. So I don't just say the Big Bang is equal some sort of a scientist experiment in a lab. It's just on a different scale. But I think that if we kind of find the real algorithm that works, then it will kind of keep going with evolution from that point. And I mean, it's a very funny thing, and I can actually recommend one thing. If you have ever seen this show called Futurama, they had a series that was called The Clockwork Origin. It's just about that, what you said. I mean, it's just about the two scientists debating like whether we have emerged from evolution or from some super being like a god, and then the one who is actually believes in evolution comes to a secluded planet because he doesn't want to have to deal with anybody who believes in creationism, so he goes to the planet, and in order to maintain his life, he kind of creates nanobots who kind of create food for him and do all the stuff, and it starts to kind of, you know, emerge so rapidly that at a certain point he wakes up in the life where there are hundreds of robots and huge cities, and he comes to the place where they kind of debate whether the synthetic life has originated from the chaos or there was some sort of a creator, and he runs in the room and like, come on, I have created you a couple of days ago, and they go, wow, he's a creationist theory. And we kind of at that very point, this is a very humorous situation, but it implies exactly what I said. It's kind of a clever, you know, experiment in a way. So yeah, I think it somehow clarified what I meant, or at least to a certain extent. Well, watch this series, maybe you'll like it. Okay, thank you. If there are no more questions, I'm very thankful for your engagement, and I'll see you on the seminars. Bye.